If there's no more questions, then I'll hand it off to Yep.
Thank you. Okay, assessing accuracy of wind-aloft forecasts. We've chosen this as our project technical presentation because as part of our increased focus on improving the analysis on our rocket's trajectory, we like to have wind-aloft data. Now, wind-aloft data, so wind varying with altitude, has been supported in RocketPy for a while, and it has several utilities for reading and visualizing this data. Recently, the OpenRocket beta has also incorporated wind-aloft data. So this is interesting to Rocketeers on ascent because we can see whether there are any severe wind shears that might cause. So right now, the stability at launch rod is the most critical parameter. Essentially, if you assume a constant wind throughout the flight, and the rocket makes it past the launch rail safely, then the assumption is that it will continue to be safe throughout the flight, as long as its stability remains within certain bounds. The concerning thing is the stability at burnout, at its highest point. And if there is a large wind shear at that point, then that could cause the rocket to suddenly change its direction. So, all of that is to say, we are interested in wind-aloft data and how accurate the different data sources are. And those data sources primarily are National Weather Services. We're going to be focusing on NOAA, just because the services have slightly different formats, so keeping it to one simplifies all of the code. And the reason we're doing this analysis is because we're not aware of anyone having analyzed its predictive power. So you have this wind-aloft data, but we don't know what that translates to. Like, all models are wrong. We don't know how wrong this one is. Our alternate candidates for a podium session would be the MATLAB and OpenRocket integration and the fin optimization and Monte Carlo analysis that resulted from that, or the removable bulkhead. And both of those are reasonably uncommon and useful for rockets, but this, of those options, is the only one that is completely novel to our knowledge. So we're looking at 6 data sets currently. We have the global forecast system at 3 different resolutions, the North American mesoscale model at 2 different resolutions, and the high resolution rapid refresh. And these models differ a lot in a few ways. They have different lateral resolutions, so how finely spaced the data samples are per wind, varying from a degree longitude, or about 100 kilometers, to 3 kilometers. They have different refresh cycles, so there's a limit on how up-to-date the data we can expect to be on the day of launch, or high resolution, the historical data we'd have from that launch site. And they have different forecast extents. This is less relevant for us since we don't expect to rely on, in the field, on any data older than about 2 days, or forecasted out to more than about 2 days. And for historical data, we'd be looking at the analysis output, so the 0-hour forecast anyway. So, I mentioned the temporal resolution. Essentially, what you can see in the graphs are the different publishing cycles of the models. So at the top, you can see the global forecast system at its low resolutions. It's published every 6 hours, and every publish has 3 hourly data. The quarter degree global forecast system and the North American mesoscale models are published every 6 hours, and every publish contains hourly data. And finally, high resolution rapid refresh, as the name suggests, is rapid refresh. It's refreshed every hour, so every hour you get 48 hours of forecast data. One very important thing worth noting here is that as you go down, the data requirements get very intense, and I'll touch on this later. Next up, we have the lateral resolution. So on the left side, we have the lateral resolution overlaid over a couple of degrees, latitude and longitude, centered around the Midland launch site. We can see the global forecast grid points as circles of varying color and size depending on the resolution, and the North American mesoscale model as that grid of little pluses. If we zoom in around the Midland launch site, we can begin to see the high resolution grid, the 3 kilometer grid. And the important thing to note here is that that circle on the map is 2 miles in radius, because every rocket we've recovered has been within 2 miles. So we expect the resolution to matter a lot for us, since that circle covers a few points from the high resolution model and no points from any other model. So we're going to need to rely on the accuracy of interpolation between a lot of the points to get accurate wind data. Finally, these models are all vertically sampled, essentially the same. Basically, for meteorological reasons, they're sampled along layers of uniform pressure, because that's more informative on a chart, and because somehow the equations of motion are simpler along an isobaric surface. What that means for us is that the geometric height, which is the variable that we'd be simulating against in our trajectory simulations, is not uniform with pressure either in time or with geography. So sampling into a specific point in space-time requires lateral sampling, time sampling, and then only then can you actually sample into the vertical coordinate. And also touch on how this is, the graph there shows how this varies from the international standard atmosphere. That has implications for both our trajectory simulation and our flight computers. So this is a sampled air column, and the left three graphs have their comparison to the international standard atmosphere. So OpenRocket does make a correction for the launch site temperature and keeps the lapse rate, so the reduction of temperature with altitude, constant from that point. But still, the atmosphere at the launch site is not a standard atmosphere. So incorporating this into our simulations will make them more accurate, and will make our assessments of what our altimeters will read more accurate, because the altimeters all assume a standard atmosphere. Finally, on the right, we can see the wind column. So that's the wind shear at this specific point. I think this is Midland at some point last year, and its variation with altitude, and the 20-mile-an-hour no-go overlaid on it. So we can see that the wind speed is not consistently higher or lower than that point, and it doesn't have a super consistent direction either. With all of that background done, let's get to analyzing its accuracy. Essentially, what we'd need to assess the accuracy of wind data is a large data set of objects that drift with the wind. And for that, we use radiosonde trajectories. Essentially, National Weather Services launch high-altitude weather balloons to gather wind-aloft data. And they publish sort of summarized version of their outputs, their wind speeds at various pressure levels. But the raw location information is actually aggregated by amateur radio enthusiasts and stored on SondeHub, which is the website that tracks and predicts the landing sites of those radiosondes for later recovery. And that gives us a bevy of data that we can use to assess the wind model's accuracy. Essentially, we simulate the radiosonde's ascent, compare that with the actual measured ascent, and develop an estimate of how quickly the model drifts from the actual trajectory. Important thing to note about the radiosonde data is that because it's sampled by amateurs, it's highly irregular. So the initial altitude varies a lot, and the descent rate especially varies a lot. What is consistent is the ascent rate, though, which is why National Weather Services typically just take the higher level data from the ascent, which is the most consistent, and discard everything else. So we got the best. We assessed here two different cases. One is a 12-hour forecast. So we pulled the historical record of a forecast 12 hours before the launch cycle, forecasted out to 12 hours in advance. And essentially, this is kind of a realistic forecast that we'd be able to access in the field. So this judges how accurately we'd be able to judge the rocket's landing site half a day in advance. So pulling, for example, a forecast the night before. And what we see is that the models, especially in those early integration times, these integration times are reasonable for a weather balloon, which can ascend for a couple of hours. We're really focusing on the first 5 or so minutes of that. And we see that all of the models are very similar at that point, and they all have a square root characteristic that is common to random walk models. So that gives us kind of a performance metric that we can use to more precisely assess the accuracy of the models going forward. The models all have about 400 meters of average error, and we're probably going to modify that to spit out a circular error probable instead of an average error. But essentially, this suggests to us that the data is useful in the recovery sense for assessing how far the rocket will drift, and this will let us form more accurate link budgets, but it's not useful for getting a landing site to then go search for, because 400 meters circular is still a very large area for humans to walk over. We also did the analysis output, and essentially why this is useful is we can look at historical analyses of a launch site and to try to figure out the weather patterns. So we're interested both in the forecast accuracy and the analysis accuracy. And we can see that the analyses, as you would imagine, improve on the accuracy quite a bit. And here we actually see the pattern we expect, where the high-resolution models perform better. There is a lot of planned work ahead of this. Although it is worth noting that the bulk of the work up to this point, generating these graphs, has been in writing a tool chain that lets us conveniently download and process this data. Because the real key thing here is that this is a lot of data we're talking about. We're eventually going to analyze thousands of radiosonde flights over much longer time scales. And right now, this equates to filling up a 1 terabyte hard drive with forecasts and trajectories. So the tool chain that lets us make use of that has been the hard part up to this point. And that'll let us do all of the planned analysis going forward. So we're going to we're going to control more tightly for the altitude. And that'll let us assess how accurate the model is at different altitudes. Because there's reason to expect that at both higher altitudes, where the models end up hitting their boundary layer, and at lower altitudes, where the surface has more of an impact, to be less accurate than sort of mid-altitudes. We're going to integrate this data into OpenRocket. Our two options for this are to use the write a custom extension, that's one we're leaning towards, and to use the OpenRocket 24 beta, which allows for wind-aloft inputs. But we're leaning towards the first option because it's more flexible, and it'll let us customize the atmosphere itself. And as I mentioned earlier, the standard atmosphere is not actually standard. We expect our atmosphere to be different from the standard atmosphere by quite a bit. Finally, we're going to expand support in this toolchain for ensemble models to feed more realistic variability into our Monte Carlo simulations. So, to summarize, we have a bunch of forecast outputs that we can potentially use. We're going to assess which are most useful for us, balancing their data cost as well, and we're going to incorporate that into our rocket's modeling to determine how many effects it has on the ascent and descent of the rocket.